Let's go ahead and just get started. This is the advertising portion of this talk. So we have been spending a lot of time in my group really thinking through improving variational Monte Carlo using some of these machine learning architectures. And so one aspect of that I'll talk about today is really how do we build more accurate ansatz that just get higher accuracy. And there I'll talk about fermions today, and we've been doing a lot of work on gauge theory. Gauge theory is particularly subtle because if you screw up the gauge symmetries, it's kind of a disaster. If you screw up translational symmetry or something, you can just hope that your ansatz restores it largely. You screw up the gauge theory, though, you'll just get physically incorrect answers. We've been doing a lot of different work in this space, thinking about how we can build wave functions essentially for the thermodynamic limit. So this is work with my former student, Dimitri, and some others. And there, the question is the following. We'd really like to get answers for very large systems. And one way you can do is correct finite size effects. But another thing that you can try to do is just build ansatz that work for very large systems. And really the bottleneck to that is optimizing them. And so really you'd like to train on tiny systems and translate those parameters in some way, shape, or form to larger systems. And so we've done this using sort of convolution neural networks or graph networks as a way to take trained ansatz on tiny systems and get them really to work for large systems. We've been excited about variational quantum dynamics of various things: open systems, quantum circuits, closed systems. And this is work that I've been doing with a couple of students, as well as a little bit with Juan Carasquala. And one of the sort of novel tricks that we've been doing there is the following. Typically, when we work in sort of the variational quantum Monte Carlo community, what we do is we say, well, we're going to try to compactify or represent the variational wave function. And sometimes that's difficult because there's all these positive and negative signs, possibly complex amplitudes, depending on what you want to do. And here we're using a nice approach. There's actually a nice mapping, a basis mapping between all quantum states and probability distributions, even states with negative amplitudes. And then there's a whole industry of people, right? A whole industry designed to compact probability distributions of cats on the internet and things. And we can just sort of take that machinery and use it to compactify the probability distribution that represents a wave function or a density matrix. And then we can actually do quantum dynamics, sort of not forces and protons and things, but real honest sort of quantum dynamics in this framework where we time evolve the variational wave function locked to some manifold. We played with something similar where we're doing some variational work to sort of store the full space-time path. The other thing we've been excited about in this space is we have sort of a finite temperature variational approach. We're starting to use it with machine learning wave functions, but it's more generic. You can think of this a little bit like density matrix, FCI QMC, or a little bit like METS, if you're familiar with any of those machineries. But this is a way to do finite temperature calculations in a variational way that we think is pretty cool and powerful. Okay, so this is the second slide of advertisement. So this is beyond kind of the machine learning approaches. We have a new technique to do optimization that I'm pretty excited about. It essentially, if you've been doing something like stochastic reconfiguration, it gives you all of the quality of stochastic reconfiguration, but none of the pain. So it's linear in number of parameters, and you don't have to build up S matrices, and you don't have to invert anything, but it gives you the variational imaginary time path, and so that's fun. We've been doing some work on optimizing basis rotations for mitigating sign problems. So this has sort of been lore in the community forever, but there hasn't been good algorithms to do it. We have a good algorithm to find smart single particle basis rotations that's extremely efficient. And we found something cute on the Hubbard model. So there's actually sort of a nice basis rotation on the Hubbard model that makes things a little bit better. Doing some machine learning for STEM. And then we've been doing a lot of various quantum computing stuff, shadow tomography, simulations on quantum computers, putting tensor networks on quantum computers, things like this, better qubitization, better VQE, and a little massively parallel DMRG. So again, this was just advertisement. This was just to throw things out so that if these are things that excite you, you're free to sort of come up and or virtually chat with me a bit later. Okay, so now for the main part of the talk, really what I want to tell you about is machine learning wave functions, and particularly for fermions. And so what's the game here? Well, the game is roughly the following, and this is really pioneered by Giuseppe and company, and they went ahead and sort of did it for fermionic states as well a bit later. But the game is they give you some configuration where your electrons are, what your spins are, et cetera. It goes through something. Originally, Giuseppe and company did with an RPM, but it goes through something, let's say a neural network, and spits out an amplitude. And so this is a black box. We can think of any such black box as a generic variational wave function. And we can say, okay, then we just should optimize everything and see how it goes. Okay, and so one can go beyond that, and there are sort of improvements or different things one can do. And one thing that people have historically tried is said, look, this is fine and all, but it capture fermionic things is a little bit difficult. I mean, it can, in theory, capture negative amplitudes, but somehow the structure of a determinant is fairly difficult and fairly subtle to capture in this framework. And so what you could imagine doing is you could say, look, let's just take a determinant and use the machine learning architecture, the RBM or the neural network, instead just as a fancy Jastro. And so this was originally done by Amada and company, and Federica and Juan and company generalized it to work with projected states. And there, again, the game is, it's a Slater Jastro, but instead of the Jastro, you're going to do e to the minus some RBM, or we'll talk a little bit later about taking the determinant and multiplying it by some neural network. So if you want, you can really treat this as an honest Jastro where it's strictly positive and really you're not altering the sign structure of your wave function at all. But it's also the case that your neural network could allow from negative amplitudes, your RBM could have complex amplitudes, and you could modify the sign structure a bit. I should say I'm mainly someone who runs on a lattice, and so most of these things are applicable both to the lattice and continuum, but the work I'll be primarily talking about is sort of lattice-based, so both spin systems and fermionic systems. Okay, and so what we've done is we've said, look, can we do better than this? Can we sort of go beyond just dressing the Slater matrix with this single number that's generated from a neural network? And so we play the following games. We call this neural net backflow. And this is obviously inspired by those of you who know from the way that backflow is treated in the variational Monte Carlo community. So backflow is done both in the continuum and the lattice, but this is very inspired by sort of what's done in the lattice. And so the game here is the following. Typically, if you have some Slater matrix, you just have some fixed set of single particle orbitals. And from that set of single particle orbitals, you can go ahead and evaluate your determinant for a given configuration. And so now the way that you should think about this, or I think the most fruitful way to think about this, is to imagine that you have a configuration-dependent set of single particle orbitals. So I give you some configuration, double occupied, spin up, spin down, and the set of single particle orbitals that are relevant for that configuration might be different than if the second site was doubly occupied. And so this is sort of a glorified Slater determinant, but it allows you to introduce a significant amount of correlation. And so then the question is, from where are you going to get these single particle orbitals? And the game we're playing is that you take yourself some machine learning architecture. In our case, it's a feed-forward neural network, and it eats the spin configurations, goes through some number of layers, and you get your single particle orbitals. And then you do the thing you typically do. You select say this is upspins, you select where the upspins are, you generate your determinant, and you take the determinant. All right, so this is the game. And okay, in practice, what we at least originally were doing is you produce a single determinant for your upspins, you produce a single determinant for your downspins, and you add on a Jastro. In retrospect, we didn't know this at the time, but the Jastro seems not to matter very much in practice. And you can ask, what is the cost of doing this? And it turns out that this is the sort of biggest failure mode in some sense in doing this. And the cost roughly is, let's say you have m hidden neurons, something either like m squared times ne or n number of electrons cubed times ne. So this extra any is coming from the fact that you're doing one particle moves. If you think you can get away with all particle moves, then you can drop a factor of any here. So this is expensive. It's sort of a factor of any more expensive than standard Slater-Jastrow approaches, and that can get problematic, or possibly even more if you're using a huge number of hidden neurons. And so that's in some sense what I would say is the biggest downside or failure mode of this approach. What you'll see in a minute is actually you can get quite accurate results, particularly if you're willing to sort of crank up the number of hidden neurons. All right, are there any sort of questions at this point?
Any questions? No.
Okay, great. And so I'll show you different variants of this in a minute. I'll show you sort of benchmarking of how we do. But let's just sort of ask, what's a little bit going on here? So this is most of the things I'll show you are just sort of benchmarks on 4x4 Hubbard models, although we have data on some bigger systems. So just a couple things to point out. So one thing we did is we just sort of opened up the hood and we asked, look, can we stare at the neural network and interpret at all anything about what it's doing? And the short answer is not much, but this is the set of weights between your input, your electrons, and the hidden layer. And the one thing that sort of does transparently come out of this is the following. The spin-up neural network really, really cares where the down electrons are. So this corner is like spin-up neural network, down electrons. This corner down here is spin-down neural network, spin-up electrons. And so there are just very strong weights corresponding to sort of that thing. It's a little funny. We have a Jastrow on here as well. So you'd think the Jastrow would be sort of doing whatever kind of job you might want to keep things apart. But that seems to be the like zeroth order thing that's going on. When you only have a couple hidden neurons, it just is really paying attention to the opposite spins. The other thing we asked is the whole sort of motivation from this is we really wanted to go beyond just a Jastrow where you aren't altering the sign structure. We really wanted to do something that changed the sign significantly. And so we just measured it, right? Some prototypical average sign. And so we see kind of a 9% change in the signs. And so we thought that was pretty good. That this really is making a difference, not just in some subset of amplitudes, but actually non-trivial in the sign structure. Okay, and so after we sort of developed this technique, there's lots of really nice works that sort of have built upon this idea. Broadly speaking, there's a bunch of really great works that have generalized this to the continuum. And there's difficulties in how really you're going to build up these single particle orbitals, how are you going to deal with Laplacians and things like that. So those were all sort of dealt with in these works. And then we did sort of this Slater determinant and some BDG work I'll tell you about. And then there have been a bunch of papers that have looked at sort of standard generalizations, doing multi-determinants, doing larger sort of determinants that contain spin up and spin down at the same time. There's this recent nice work from Giuseppe and James and company doing a constraint hidden that is sneakily of this ilk as well. And I'll tell you a little bit more about that later. And so, okay, these papers actually do lots of other things. These are much deeper than just this, but these were the first people that did some of these variants, although often in the continuum. Okay, and so this is, I'm going to tell you sort of about the zoo of variants of this so that we can really understand what's going on. And this is roughly sort of the relation. So neural net backflow is what I described. There's a BDG version of this, like a superconducting BCS version of this that I'll tell you about in a moment. And then there are various other things. There's kind of basic Slater determinant. If you can do multi-determinants, probably doesn't win in the thermodynamic limit, although there's some interesting features of it I'll tell you about in a few minutes. There's this constraint hidden work recently by Giuseppe and company that's kind of sneakily a subset of neural net backflow as long as R is small, the number of auxiliary fermions is small. I'm building this diagram. There's some cheating in this diagram. I'm assuming something about how well each matrix element can be filled out by the neural network. Okay, so let me tell you about a couple of these variants because I think it's sort of important to know kind of the zoo of options and to understand how they're related. So the most natural thing you can do is you can say, look, there are mean fields beyond Slater. You can just build up some BDG state. And there we play almost the same game. So you're eating spin up and spin down wave functions and locations, configurations, and you're building essentially the BDG states. You build up the spin up single particle orbitals, the spin down single particle orbitals in this S matrix. And then from that, you can build up your pairing function directly. So this is sort of a natural generalization. You'll see in a moment, it gives you a lot more power if you have a couple neurons. As you crank up the number of neurons, you introduce correlation in all of these methods. And so some of the extra power goes away. There's also another approach here. You can sort of, instead of doing spin up and spin down determinants, you can do one larger determinant. And Lin and company were sort of the first to play with this. And so this helps in some contexts, in some cases. You can also do multi-determinant expansion. I'm generally not a believer in multi-determinant expansions, particularly for Gnode systems. So we're interested in Hubbard models, frustrated magnetism, things like that. This case, it probably still doesn't help in the thermodynamic limit, but there are some interesting things going on that I don't understand. And so typically you expect, you need a fairly large multi-determinant expansion before you see things. And as I keep adding more and more determinants, I get kind of a little help each time. And so what we did is we went, and this is sort of more recent work that Zhejian's been doing, we went and we optimized some multi-determinant expansion, 4 determinants, 8 determinants, et cetera. And as we optimize more and more, like all of the bigger determinants essentially just fall out. So this is the amplitude of each determinant, essentially how important each determinant is. Okay, you have 4 determinants, it's falling slowly, and this is fine. But you have 8 determinants, and determinants 6, 7, and 8 are just completely irrelevant. Like they give you absolutely no help. So I should say these are weird determinants, right? They're determinants where each determinant independently has a complicated neural net backflow sitting on top of it. And there's a huge amount of correlation in them. But it's still surprising me that these determinants are sort of falling out. And in fact, earlier in the optimization, we only had, we had determinant 6 and 7 and 8 fill out. As we sort of worked harder and harder on our optimization, more and more determinants are disappearing. And so I think there's sort of an interesting open question to understand what's going on there. And the extra determinants, they give you sort of some amount of help. So here, as we go from 1 to 4 to 8, these are sort of 4, 5, 4 Hubbard models, U equals 8, filling a 0.875. This is sort of a fair comparison. And then we did something where we optimized things sort of better. And it's still the case that as you like crank up the number of determinants, you get a little bit better. So they're not irrelevant, but also they seem to run out of steam quite quickly. Okay, so now let me really show you some results. So a couple of things here. So this is, again, 4x4 Hubbard. So small benchmarks where we know the exact answer. So if you just do a Slater Jastro and optimize all the single particle orbitals, optimize all the Jastro, you get something like a 5% error. Doing BDG gains you a little bit. So maybe you get, I don't know, 4.5% error. So now if you come in and you're like, look, I'm going to do neural net backflow with very, very few determinants. Nonetheless, you already win. You sort of win by a factor of 2, even if you're using, sorry, not determinants, very, very few hidden neurons. Even if you're using very, very few hidden neurons. So I don't know, 4 hidden neurons or something. You're already sort of gaining a large win. This is for the Slater determinant. And then if I turn on the BDG, well, things get sort of much better. You go from sort of a 3% error to a 1.5% error. And then as you sort of crank up the number of determinants, things kind of get systematically better, not surprising. And this is still using very, very few determinants, so few hidden neurons. So this is using 64 hidden neurons. In a minute, I'll tell you, sort of use 1,000 hidden neurons, like it's much, much better. But let's just look at this data for a second. So as you crank up these things, the percent goes down. So here you're down to kind of 1.5%. And you can go ahead and do variance extrapolation. I always have a tendency to try variance extrapolation, and it just never, ever works for almost anything I do. You do multi-determinants, you do all sorts of things. It turns out with these neural net backflow, the variance extrapolation is just much cleaner than I've ever seen it before. And so we actually get sort of reasonable variance extrapolation down to kind of a 0.5% level. So this, again, is all with 64 hidden neurons and nothing too large. You go up to sort of 1,000 hidden neurons. And I mean, you're essentially, errors at kind of the like 0.2%, 0.02% levels that you're beginning to reach. And so this is not too expensive to do. We didn't do it in our original work because we didn't have a GPU code at the time and we weren't on big machines. But now you can sort of, without too much pain, go up to thousands of hidden neurons, and you get very, very accurate results here. Okay, so not only can one go ahead and look at sort of the energetics, one can ask some questions about what the neural net backflow is doing. And so by looking at various observables and various aspects of the wave function. And so one thing that we see very clearly is as we crank up the number of hidden neurons, what ends up happening is we get a lot of the symmetry restored. So that's true in the observables. So the charge density goes from something that is not at all symmetric to something that is much more symmetric. Same thing with the spin density. You get the kind of correct staggering. But also, like, even if you peer into the wave function, things get much better. So what are you looking at here? You're looking at the single particle orbitals. This is just the best Slater Jastrow we know how to optimize. This is the spin up single particle orbitals, and this is a spin down single particle orbitals. This is just the heat map. And what you see, if you stare at it for a minute or two, is they look quite different. Not too surprising. The electrons want to stay out of each other's way. The Jastrow is doing a little bit of that work. But these single particle orbitals are also doing some of that work. And so you end up having a breaking of the symmetry that you know should be there. You can now go back and you can look at the same thing for the neural net backflow. Okay, there's not one set of single particle orbitals there. There's a configuration dependent set of single particle orbitals. So all you can do is you can take some prototypical snapshot. Here's some configuration that's kind of standard. And if you look again at the heat map of the single particle orbitals for this prototypical snapshot, qualitatively, they're very, very similar. I mean, there are quantitative differences here and there, but they restored a lot of the spin up, spin down symmetry that had been destroyed before. We can go back and we can go ahead and we can do much larger systems. So 16x4 Hubbard models, 12x8 Hubbard models, et cetera. 4x L Hubbard models, and what we see is we get quite good results. So on these larger systems, our errors, and this is very few hidden neurons now. So this is older results. We can crank up the number of hidden neurons with more now. Then even at the time, we were able to get sort of 0.2, 0.6% errors. If you do something like 4x L Hubbard models, you can do 4x4, 4x8, 4x12, 4x16. And then you can compare against, say, 4x infinity IDMRG. And we're really sitting right on that line. The 4x12 is off because it doesn't have the right appropriate wavelength for Hubbard models here. But the 4x8 and the 4x16, which do have the right wavelength, are really sitting on the IDMRG line. So this gives us some confidence that we're really sort of probing and reaching sort of the level that one can get with things like DMRG, auxiliary field, things like that. The other thing worth pointing out here, and the other thing that I think is kind of exciting, is if you ask people who have done backflow historically, if you're like, look, where should backflow work the best? Roughly what they're going to tell you is where there are lots of particles and holes. The standard backflow formulations depend on sort of the particles and holes. And so places where you have sort of, let's say, a frustrated magnetism system where you're exactly at half filling at all times, there's no particles or holes ever, you would expect that it would be pretty crummy. And yet, on something like the 4x4x3 Kagame system, which is a horrible beast, and I mean, you can get variational energies down there if you do DMRG, you can get variational energies down there if you do sort of Lanchos method a la Sorella, but no other sane sort of variational ansatz has really gotten low energies on this state. And here we're getting sort of kind of state-of-the-art energies with variance extrapolation that's very, very good. And so even in the case where you're kind of exactly at half filling, things are quite good. Okay, so now where I want to move is to ask the following question. We've talked about some various fermionic techniques. I've told you about a neural net backflow. There's also this Slater RBM or Slater neural net, where you sort of dress the determinant with some amplitude output of a neural network. There's this Slate fermion or a constrained hidden approach to fermions that Giuseppe and James came out of. And can we somehow unify this in a general framework and think of these as existing on some continuum? So why don't I pause for a second and ask if there are any questions?
So, Bryan, maybe a question about the Hubbard stuff, symmetry restoration.
Yeah.
So you show the charged order, which with more neurons got restored, and then you have a essentially perfect anti-ferromagnetic pattern.
Yes.
Is that worrying? I mean, ideally, your function would have zero spin, even though it has a strong spin correlation.
Oh, because you would really restore the translational invariance.
Uh-huh.
Yeah, no, we're not that good. I mean, you're right. There's a translational invariance you should restore up and beyond sort of this kind of symmetry restoration. That's true, but we're not. The wave functions are not that good to get that level of symmetry restoration. So we get a lot of the symmetries back, but we don't completely restore the translational symmetry so that you don't have some spontaneous symmetry.
So my worry is, how do you know that it's not in an in-between state? You know, it's okay to not restore the symmetry if you're exactly in the symmetry breaker state. Like how we do these, we put a pitting field, we just break it, and then we know we're trying to go after a spin pattern. But if your Jastrow is doing a lot of things, and the neurons are doing a lot of things in the determinant, and yet you're ending up with a broken symmetry spin order, could that be worse than, you know, could that be stuck in a halfway between a symmetry broken state and a fully symmetry restored state, and therefore be, you know, give you misleading information about the system?
I mean,
by 4, this is less relevant, but when you try to extrapolate the bigger system, that works.
yeah, so right, that's what I would say. I would say it's possible, but I'd be very surprised. And as our systems get longer and larger, I'd be extremely surprised. So I doubt that we would be in such a situation, but I can't formally rule it out. It's of course possible that that would happen, and the observables would sort of in some sense be worse, even though we were much lower energy and everything looks thinner. But I'd be surprised if we run into that.
Yeah, you do have the latter results, so presumably you they might just be perfectly fine. They might be giving you the correct stripe states with a 4 by 16 type of states. I don't know if you looked at those or not.
I mean, a little bit, and my recollection is that like everything looks essentially right, but we have not looked at it carefully enough that I would want to say that with high confidence at the moment.
Thanks.
Particularly because I think even with standard Slater Jastrow, we get very similar things with respect to the latter results, but that's sort of a bit of a longer story. Great. Any other questions?
I have a quick question about the slide. So part of the presentation was covered with some things I can see, but when you showed that adding additional backflow didn't change that energy at all, how far were you from the exact energy?
This is additional determinants, isn't changing the energy at all. And at that point, we're kind of at the like 0.3% difference.
I see. Okay.
They're not enough where like we are right on top of it, but still nonetheless pretty close.
Okay. Thanks.
Okay. Any other questions?
So a higher level question is, earlier you mentioned that you're not a believer of multiple determinant expansion. What's the alternative? And maybe I missed that.
I mean, I'm just not a favor because in the thermodynamic limits, sums of wave functions tend not to be very fruitful. I mean, I guess for any finite system size, it's fine. And so it's just sort of like, if I'm doing chemistry, it's great, right? But if I'm doing some condensed system and want to go to a large size, it's just not size extensive. I think the alternative is that you just have one determinant and you like crank up the number of hidden neurons in our neural net backflow or something. But right, I don't have a deep answer for you. It's just sort of an unprincipled this is not size extensive, and so you have to be a little bit careful what you're doing. I've written lots of multi-determinant papers, so I'm not like morally opposed to it. It's just, it's not something where you expect to win a huge amount in thermodynamic limit.
So it's in that context, related question. So when you do these backflows and you want sort of similar percentage error, do you find that the number of hidden neurons, how does they scale with the size of the system? Do you have an idea?
I think the answer is roughly that you want the number of hidden neurons to stay linear with the number of input neurons. But again, we're beginning to do some more systematic studies of these things. I would not say that with much confidence yet.
Okay.
Great. Additional questions?
I think that's all, but
Okay.
do you have about 10 more minutes or?
Great. Yeah, that sounds good. So now what I'd like to do is really think about sort of the space of fermionic wave functions. And so we have neural net backflow living out here, and Slater RBM living out here, and this slave fermion or continuous hidden thing living somewhere. And so can we sort of put these on some continuum? And so one thing we can imagine doing is saying, look, really the neural net backflow we can think about actually as the Slater determinant times some n by n matrix that we're multiplying by. It's a perfectly fine way to think about it, just some Woodbury kind of algebra here. And we can think about the Slater Destro as taking the Slater matrix, the Slater RBM or Slater neural net is taking the Slater matrix and multiplying by the determinant of a 1 by 1 matrix. So some generic n by n matrix. And so now we can go ahead and we can just generalize this, right? Say, look, let us imagine that really what we have is we have the determinant of some Slater matrix, and then we're going to multiply by some determinant of phi, some generic R by R matrix. And that generic R by R matrix is going to be generated somehow by some neural network. And so this gives us sort of a continuum. I mean, in some sense, if R is less than N, you're still going to want to do neural net backflow, but it at least helps us start to understand kind of the space of fermionic ansatz. And in addition, if you can get away with smaller R, this evaluation of this determinant was actually the costly thing in our simulation. And so actually you might be able to do simulations that are faster, even with more particles. And so now what we should do is we should think of kind of how is it we want to build this R by R matrix. I mean, so one thing you could do is you could just say, oh, my neural network is going to generate an R by R matrix. That's very general, and I think for deep enough networks and smart enough networks, that might be the way to go. But it's a little bit painful to optimize that, and it doesn't really look like neural net backflow when R is N, because in the neural net backflow, you're doing some sort of selection, right? Remember, we built the single particle orbitals and then we chose them. So if you really wanted to do some sort of minimal modification, what should you do? Well, this one was sort of like phi inverse times n times some mask matrix that selects your configurations out of your single particle orbitals. But the problem is this doesn't have the right dimensions. It's not R by R. And so essentially you just need to like pad the ends of this thing. So you say, I'll pre-multiply by an R by L matrix. So now it's got dimension R. I'll essentially post-multiply. Well, I don't even need to post-multiply because there is a matrix, a set of single particle orbitals that's being generated by the neural network. So instead of that being the size it was, I'll just make it the size that I need it to be to make this an R by R matrix. So this is sort of one very reasonable natural way to sort of generalize neural net backflow to spit out not n by n matrices, but generic R by R matrices. And so we can do this. This is some decay of imaginative evolution. We're using this new optimization we have, this SWO, that I really think is very powerful and more people should be using. It's working quite well. What do we find? Well, not surprising, we find that at R equals 1, this is morally equivalent to doing the thing over here, to doing Slater neural network. we do R equals 1, we get a fairly high energy. And as we crank up R, things get better. They get better actually quite quickly. I mean, this needs like a 14 by 14 matrix to be sort of the standard neural net backflow. And even by the time you're at a 3 by 3 or 4 by 4 matrix, you've already restored a lot of the energy. So if your goal is to be fast, it turns out that you can actually get most of the energy that you're going to restore by doing a much, much tinier matrix. And then as you go past 14, you don't win at all. This surprised us to begin with, but it actually turns out that if you just think a little bit, what this minimal modification is doing is really it's assuming that the single particle orbitals in a standard neural net backflow are low rank. So this assumes that they're rank 1, this assumes they're rank 14, and eventually, I mean, you're full rank, and so you don't win it anymore. So this is a sort of a neat way to extrapolate between the standard kind of just, oh, I'll multiply by a neural network and the neural net backflow. And we can do other things. You might say, well, here's some formula and there's an identity in my formula. I might as well make that a parameter, right? Might as well make that, instead of an R by R identity, some R by R matrix. And so if you do that, actually you just get something else, right? But what's really interesting is, although this isn't sort of manifest in the work, there's this really nice work by Giuseppe and Antoine George and James Stokes and company. And they have this slave fermion story with these constrained hidden states and this really nice picture. But if you just sort of open up the box and ask, what are they doing in their ansatz? Well, essentially, what they're doing is they're taking a determinant of the Slater matrix and multiplying it by an R by R matrix, where R is this auxiliary slave fermions that they've described. And it's not described this way in the paper. They actually are working with much bigger matrices ostensibly, but actually you sort of do the right algebra, think about the, sort of the Woodbury formulas in the right way. And actually what you see is that these constrained hidden states are really just the Slater determinant times an R by R matrix. And so in some sense, a subset of the standard neural net backflow. And so that's sort of a nice way where you can take and kind of think about all of these different ways of doing fermionic wave functions and really describe them on sort of this continuum of determinant Slater matrix times some R by R determinant all the way out to n by n. Okay, so I have like a minute left. Let me end here and then I'll skip sort of the gauge theory stuff. Where are we? Well, what we see is that multiplicatively modifying the Slater determinant by some R by R matrix is, one, quite accurate, and two, really gives us a unifying view of many of the neural net frameworks out there, not neural net, fermionic frameworks out there. And it really, in some sense, tells us that if you do something like neural net backflow with BDG, that if you can get away with optimizing it well enough, that is sort of essentially as best you can do at the moment. It's sort of one fermion method to rule them all. So what are the things that we don't fully understand that we're still sort of working on? Well, there's still sort of an open question on how to fill out this R by R matrix. So one thing you might think is, well, my feed-forward neural network should just spit it out. And sort of we know that very naively, if you only have a shallow feed-forward neural network, that's not a good thing. So here we have sort of energies for that, and that works very poorly. And we really understand why this is. You really need sort of this selection of the single particle orbitals. You need somehow phi inverse to be embedded as part of your input. And so we think there's a way to do this with deeper networks that will sort of allow further optimization and capture all this, but sort of the naive thing doesn't work. The other thing is probably for kind of L by L matrices or N by M matrices, the neural net backflow approach, I speculate, but have some reasons to believe, is probably sort of a very good way of filling out your determinant. What else do we understand? Well, this is all for sort of 0 to L, or 0 to number of electrons. Suppose we push the R to something bigger than the number of electrons. We know places where that doesn't help, but we think generically it should be able to help, and there's sort of an open question for how much. There's this odd question about multi-determinants in practice that we don't deeply understand. And in particular, we don't have we have some understanding now, but not a complete understanding of, do these other variants help you as I crank up the number of hidden neurons? BDG seems to lose some of its power compared to, say, Slater determinants as I crank up the hidden neurons. And finally, can we go beyond this sort of framework, the determinant of a Slater matrix times the determinant of some other matrix? And we're starting to look at other things, sort of multiplicative, multi-determinants, and neural net backflow and things like that. So I'm about out of time now, so I'm going to just skip all this. If you want to know about how we do variational gauge theories, which I think are very cool, we get really strikingly good results for things like tort code and quantum link models and things, even for dynamics. So come talk to me later, and I'll stop talking. Thank you.